Okay, so today's lesson is about average atomic mass. And so this average atomic mass, I'm going to highlight this piece here, average. It is not one single atom. It is actually lots and lots of atoms. Supposedly, it's all the atoms that we would see on Earth, and then it averages the weight for this particular element. Now, what we see on the periodic table is this average. And we know it's an average because it has a ton of decimal numbers. And so when I look at the periodic table and I look at the very bottom, for example, for boron, it reads 10.81. And those decimals are there because it is an average. Most isotopes have a whole number mass, or very, very close to a whole number. And so when we have an average, it's a special way of writing down its mass. Okay, so why do we need the weighted average? Notice that there's a special word here, and it says it's a weighted average. A weighted average means that not everything has the same importance. So, for example, I might be in a math class where homework is only worth 20%, but tests are worth, 60 or 70%. This means that your test scores will have a bigger impact on your grade than your homework score, and that is a weighted average. And so we're also going to be using a weighted average because not only do we need to know the mass of the isotope, we also need to know what percentage they're worth. So sometimes I might have an isotope that is 90%, and I might have an isotope that's only 10%. The 90% will have a bigger impact on the actual average. Okay, I'll pause that. I want you to imagine that everyone in class is represented by this dot. Okay, and so I have lots of dots. All right. Now, are all the dots the same size?
Yes.
We'll look carefully. Carefully. This one on the right here looks slightly larger, right? And so this one here looks a little bigger. Are there ones that look slightly smaller?
Right there.
Yeah, this one looks like it's pretty standard in the sense that there's lots of these perfect circles, right? And then there's one that are like slightly fuzzier. This one is slightly bigger, and then this one is also slightly bigger. I'd say these two over here that I've circled in these two here that I've circled in my highlighter are slightly bigger than the others. Are we okay?
Yeah.
Okay, now, are there a lot of these bigger ones? No. And so if I went around and I said, hey, you know this thing here, what if I assign it a weight? And I say, these things weigh 2, and everything else, these things weigh 1.
Wow.
Okay? Oh, no, I just want you to look. Okay. If I said, what's the average of their weight, of their mass, would you say that it's 1.5 as the average? No. It would only be 1.5 if I have the same number of 2s and 1s. Are we okay with this? If I told you that 80% of the ones in here were 1 and only 20% were 2, does that help us find the average? Kind of. So what's the average then? Is the average closer to 1 or is the average closer to 2?
Closer to 1.
And why would you say that the average is closer to 1? There are more 1s. So the average is closer to what you have more of. More percent or items. Okay? So if I have a lot of 1s, we would expect the average to be very, very close to 1. All right? So we're going to do this problem Cornell style, and we're going to write the steps of finding the average atomic mass on the left side. And on the right side, we're actually going to show the steps of the actual, like us performing the steps on the right side. Okay. So here is what we're going to do. The goal is to find the average atomic mass. This is our plan, our end goal. And the question, this is the example here on the right side, is to find the average atomic mass if carbon was 99% 12 and only 1% 13. But what does that mean? That means on our previous picture where they were all 1, most of them are 12. And only a few, maybe just 1 out of 100, is only going to be 13. That's kind of a weird situation. If we were to make a guess, what do you think the average would be really, really close to? It should be close to not 99, but it should be close to 12, because there's 99% of it's 12. Okay. So, but we actually want to actually calculate this using a calculator and not just say, well, I think the answer is going to be close to 12. I actually want an actual answer. And so this is what you're going to do first. The first step is to change all of our percentages into decimals. So this is our goal. To change a percent to a decimal, you can move the decimal 2 spaces to the left, which is the easiest way to do this, or you can divide by 100, which will accomplish the same purpose. So let me demonstrate how this works. So I have 99%. And what I'm going to do with this 99% is I'm going to move the decimal 2 spaces to the left. What do I get? 0.99. Now, if I don't know how to do this, I can divide by 100 in the calculator. 99 divided by 100. Go ahead and try that and see if it gives us 0.99, which is what we were hoping for. Okay, so let's take a look at what I have so far. I have 0.01. How did you do? Pretty good? Okay, so that's step 1. All we're doing is we're changing it into a decimal. Let's take a look at step 2 then. What we're going to do is we're going to multiply the decimal by the mass number for each isotope. Essentially, we're going to multiply by its mass. And the mass number gives us something that's very close to its mass. It's not its real mass, but it's very close. Well, what are mass numbers, Mr. Chen? These are numbers that go after the name. So when I say carbon 12, that 12 is its mass number. Carbon 13, 13 is its mass number. So what does that look like? So if I'm doing step 2, all we're doing is we're taking the percent, which is 0.99, and we're going to multiply by the mass that percent is for. 99% is for carbon what? Carbon 12. And so I'm going to do 0.99 times 12. What do you think we should do for the other percentage? Not 0.99. The other percentage is not 99%. 0.01 times 13. Because the 1% is not for carbon 12, the 1% is for carbon 13. So we're going to take the percentage and multiply by the mass that is for that percentage. Okay? This is where you're going to type in some things in the calculator. What do I type in? 0.99 times 12. I'll go ahead and let you do it. Okay, let's check back in. I have 11.88 for the first one, and I have 0.13 for the second one. How did you do? Yes? We can put it at the very end, all right? We can put it at the very end. AMU stands for atomic mass units, all right? So that's a good question. So this okay, so the question was, what is AMU? That's atomic mass units. From last time, the atomic mass unit is the weight of a proton. So 11.88 is 11.88 times the weight of a proton. Okay. What do you see as the last step here? Step 3. Add up the results. And so all we're going to do is we're going to take both of our answers, which is 11.88 and 0.13, and we're just going to add them together. And that's our final step. Once we do this, we should get 12.01 atomic mass units, AMU. Okay? And this is the average. Was this average close to 12 as we expected? Yes, it's almost exactly 12. One other thing I'd like you to check is I told you that the periodic table gave us averages, right? What do you think is listed on the periodic table for carbon? Let's find carbon. Oh. So what we're going to do is we're going to apply the same steps. Change the percent to a decimal, multiply by its mass, add them together. Okay? I'm going to give you some time to work on this, and I'll check in with you in about 20 seconds. If you're listening on the video, now would be a good time to pause and work this out. Okay, welcome back. If you change the 20% into a decimal, you should get 0.20. Whoops, I screwed up there. You should get 0.20. And we're going to multiply by the mass with 20%, which is 10, leaving us 2. And then we're going to do the same thing for the 80%. The total is 10.8. If we look on the periodic table, it says 10.81. It's very, very close. But why is it not the same, Mr. Chen? Well, it turns out that this percentage should probably have some decimals that we don't see here. Actually, the mass is not exactly 10 and it's not exactly 11. It's actually like 10.99 or like, yeah, it's very, very close to 10. 10 is close enough, but you may find that it's not exactly 10. Okay? How was this?
That was awesome. I got it.
It was not that bad. Okay, excellent. Okay, I'm going to have you do one more because I am not convinced that you know how to do this. In fact, there were maybe 4 or 5 students who weren't actually doing the work and just copying the answers from the slide. And so you're going to see this on a quiz eventually, but for sure your homework is going to have these concepts, and so I want to make sure you guys can do this. So let's try another one. Again, the steps are the same. What's step 1? Percent to decimal, then multiply by its mass, and then add them up. Okay, so you've given this a good go. Welcome back, and let's see how you did. I have a total of 35.48 atomic mass units. This is very close to the published value. The last one I want you to try looks a little bit different than the ones we've done before, okay? But I'm pretty sure you can still do this, okay? Here is your challenge problem, okay?
Oh my god.
All right. Good luck to you.
Oh my god.
I'll check back in here with in a few minutes. Go ahead and pause the video and try this one. Okay, welcome back. Let's review step 1. What is the first thing?
20 percentages.
I want to change the percent to a decimal, so that's
79
0.79. Excellent.
times 24.
Times 24.
18.96.
18.96. Excellent. Nice work. And then the second one is the same. 0.10 times 25. This one is 2.5. And then 0.11 times 26.
Equals 2.86.
Perfect. We're going to add together, and it looks like it's going to be 24.32.
0.32.
Do you have an AMU at the end?
Yes.
Nice work.
Yeah.
Okay.
Sounds like a college.